Assalamualaikum and hello everyone. Okay, for today we will cover on input, output, management and disk scheduling. So these are the learning outcomes for today's lecture. Okay, first to understand the I/O devices and the organization of I/O function. Second is to explain the I/O buffering. And the third one is to understand and explain the disk scheduling algorithms. So first we shall start with the I/O devices. Okay, so you have to know the categories of I/O devices. Okay, external devices that engage in I/O or input-output, okay, with computer systems can be grouped into three categories. Okay, there are three categories. Okay, the first one is human readable, okay, which is suitable for communicating with the computer user. Okay, for example, printers, terminals, video display, your keyboard, mouse, okay, all these are human readable. Okay, second is machine readable, and these machine readable devices is suitable for communicating with electronic equipment such as disk drives, USB keys, sensors, and controllers. Okay, while communication-based devices are suitable for communicating with remote devices, okay, usually used for network purpose, okay, such as modems and digital line drivers. Okay, these are the differences in I/O devices. There are many differences in I/O devices. Can be differ in a number of areas such as data rate, okay, where there may be differences of magnitude between the data transfer rates, okay, in terms of application, okay, where the use to which a device is put has an influence on the software. The third one is the complexity of control. Okay, different devices have different complexity of control. Okay, where the effect on the operating system is filtered by the complexity of the I/O module that controls the device. Okay, for example, complexity of control for your printers, okay, is much easier compared to the disk. Okay, the disk. So the disk is more complex in terms of control. Okay, next is the unit of transfer. Okay, data may be transferred as a stream of bytes or characters or in larger blocks. Okay, data representation also different from one device to another. Okay, where it uses different data encoding schemes. And last one is the error conditions, the nature of errors, the way in which they are reported, okay, their sequences and available range of responses is different from one device to another. So these are the data rates, okay, that are different from devices. Okay, this is the typical I/O device data rate. You can see here, the gigabit Ethernet, okay, requires more data rates. The how can I say? Okay, the largest data rates, okay, in bit per second, 10 to the power of 9. Okay, this is followed by graphics display and hard disk, okay, Ethernet, optical disc, and you can see the bottom part, okay, mouse and keyboard requires very small data rate, okay, very small data rate. So you can see here the data rate is very different from one to another. Okay, and then you have to know the organization of the I/O functions. Okay, basically there are three techniques for performing I/O. Okay, which are programmed I/O. Okay, programmed I/O, where the processor issues an I/O command on behalf of a processor to an I/O module, meaning that when a processor needs to use input-output, okay, it will make the processor issues the I/O command on behalf of it. Okay, it will issues to an I/O module. That process then busy waits for the operation to be completed before proceeding. So it has to wait until the procedure complete. Okay, this is the program I/O. Okay, the second one is the interrupt-driven I/O. Okay, this is where the processor issues an I/O command on behalf of a process. Okay, still same like program I/O, but the difference is it has condition, situation where if it is non-blocking state, if it's non-blocking, then processor continues to execute instructions from the process that issued the I/O command. Okay, whereas if it's blocked, okay, if it's blocking, the next instruction the processor executes is from the OS, which will put the current process in a block state and schedule another process. Okay, so it has two situations here. So the one is the interrupt driven. It is so similar to program I/O, but it has situation where it can be blocked or non-blocking. Okay, and the third one is direct memory access. Okay, direct memory access is a DMA module controls the exchange of data between main memory and an I/O module. Without the interruption of processor. Without utilizing the processor, it will not use a processor to issue I/O command on behalf of process. It does not use processor in between. So we shall see the difference between these techniques. The I/O to memory transfer through processor. Where there are two techniques with no interrupts and also the use of interrupts. The one that we discuss here, these three techniques can be divided into these two categories: no interrupts and also use of interrupts. If it's through processor, no interrupts called as program I/O. The use of interrupts is interrupt-driven I/O. And the direct I/O to memory transfer, through the processor, is called as direct memory access. We use interrupt as well, but it's only on the beginning and end of it. So we shall see after this. So these are the evolution of the I/O function. The earliest step is processor directly controls a peripheral device. Peripheral device refers to your I/O devices. Where anytime the process needs to access I/O, it needs the control of processor, meaning that process will control it. The second phase is where a controller or I/O module is added. The third phase, same configuration as step 2, but now interrupts are employed. Next, the I/O module is given direct control of memory via DMA. Now the control is given to DMA instead of processor. Next, the next phase, the I/O module is enhanced to become a separate processor with a specialized instruction set tailored for I/O. So it has become a separate processor itself. And finally, the I/O module has a local memory of its own and is in fact a computer in its own right. This is the advanced stage of evolution of I/O function. So as you can see here, this is the direct memory access. Where there will be no control of processor. And you can see in figure here, typical DMA block diagram. The DMA block diagram consists of data count, data register, address register, and also control logic. Where you can see here, request to DMA, acknowledge from DMA, interrupt, read and write happens here inside the control logic. So basically, this DMA unit is capable of mimicking the processor and indeed of taking over control of the system bus, just like a processor. So it needs to do this to transfer data to and from memory over system bus. So this is how DMA works. when the processor wishes to read or write a block of data, okay, it first issues a command to DMA module by sending some information to DMA module. So these are the informations include read or write request, okay, the address of I/O device involved, the starting location in memory, okay, to read or write, and the number of words to be read or written. So after giving information to DMA module, okay, after giving command and information, the processor then continues with other work, and it has delegated the I/O operation to the DMA module. So now DMA module will take control. Okay, it will transfer the entire block of data, one word at a time, directly to or from memory, okay, without going through the processor. So when the transfer of data is completed, the DMA module sends an interrupt signal to the processor. Okay, it will give signal mentioning that it has finished. So then we know that the processor is involved only at the beginning and the end of the transfer. You see, it does not involve in between, but only when it wants to, when it's wished to use to access data. Okay, it will send a command to the DMA module, and also at the ending part, okay, ending part, where if the data transfer is finished, then it will send signal to the processors so that it will continue with the control. Okay, so this is about direct memory access. So you can read the explanation of this slide in the footnote. Okay, so these are the three DMA alternative configurations. Okay? There are three configurations here. You can see here the first one, okay, using a single bus, okay, detached DMA. Okay, all of these are in one system bus, one single bus. The processor, the DMA, okay, all the input output, and also the memory. So basically, the DMA module, okay, acting as a surrogate processor, uses program I/O to exchange data between memory, okay, and I/O. Okay, memory and I/O to transfer data. Okay, and also to exchange the data between memory and I/O module through this DMA module. And you can see it's a bit inefficient. Okay, it's inefficient because it uses only one single bus to do everything. Okay, each transfer of a word consume two bus cycles, meaning that the transfer request, okay, the first one is transfer request, we'll use the same the single bus, and the transfer itself will use the same bus as well. Okay, so this is inefficient. So this problem can be solved by the integrated DMA I/O. Okay, as you can see here, all right, there is a path between the DMA module, okay, and one or more I/O modules, and it does not include the system bus. The I/O is not included in the system bus. It is under the DMA itself. All right. So this is the concept of the integrated DMA I/O, and you can also have another type of configuration where there are another bus called as I/O bus. Okay, this is especially for I/O only, for I/O bus only. All right, centralized under DMA the I/O bus. So basically there are two buses, system bus and also I/O bus. Okay, connecting I/O modules to the DMO modules using an I/O bus, and this reduces number of I/O interfaces, okay, in the DMO module to one, and provides for an easily expandable configuration. Okay, so these three different DMA configurations.